Thank you for the introduction. Again, my name is Matt Miller. I'm one of the co-owners here at EMA, and today I'm happy to talk to you about our ARM system to generate data for RF interference analysis. Before we get into the presentation, I want to spend a few moments and talk about our company. First of all, our headquarters is near Denver, Colorado in the city of Lakewood. We also have an office in Pittsfield, Massachusetts. And then we have a division of EMA in Europe, which is located close to Paris, France. EMA has deep technical experience in several areas of electromagnetics, including lightning, HRF, precipitation static, EMP, spacecraft charging, general EMI, EMC, installed antenna performance, RF interference, which is the focus for today, and radar signature prediction. So one of the things that makes us unique at EMA is our experience and expertise in these three key areas we show on the right. So we develop our own modeling and simulation software. We have measurement services and measurement systems that we develop at EMA. And then we provide consulting services for companies. And we've been doing this for over 40 years. And we've had the opportunity to work on a very wide variety of platforms, including rail systems, launch systems, satellites, aircraft, ships, ground vehicles, and a variety of other platforms. So what we learn in one of these areas tends to benefit the other major area here. So for example, when we're performing a consulting project for a customer, we'll learn about certain parts of the problem that are really critical to model accurately in our software. And so then we can incorporate that into our simulation software. And data that we collect in our measurement systems, we can also incorporate that into our simulation software to make it better and more accurate. The agenda for today is as follows. I want to spend a few moments talking about the RFI problem in general, and then go over the ARM system. And then we have 5 demonstrations showing you some real-world interference problems. And for some of these cases, we have video showing the interference and how we mitigate it. And then we'll have a summary at the end, followed by a short question and answer session. Okay, so the first question to ask is, what is radio frequency interference? And RFI is basically when a threat signal causes some sort of degradation or complete loss of performance for a receiver. And that degradation may be something like descents, it may be reduced range for a system, it can be a snap, crackle, pop in a audio comms headset, or a variety of other impacts. So the threats in these situations are intended transmitters. And those intended transmitters can be on the same platform, or they can be on nearby platforms or structures, but they're intentional transmitters. We also have to consider clock signals and the harmonics of those clock signals, which can be very problematic, as well as intermodulation products. So we show an example of an intermodulation product scenario on the right, where we have multiple signals that are present in a nonlinear device that then generates intermodulation products that can cause interference to a receiver. The way that we measure RFI depends on the type of receiver. So for example, an audio communication system, we might use the SINAD metric, which is signal to noise and distortion. And so what we would do is establish some baseline SINAD value and then look for degradation in that SINAD value as interfering signals are introduced. Or for digital systems, we might consider bit error rate or carrier to noise ratio, and for some other systems, we consider throughput. So what types of platforms experience interference? Well, we show a wide variety here, but the answer is pretty much everything. So just about any sort of platform where we might have multiple RF systems on board, has potential to experience interference. And this includes things like modern vehicles, like this vehicle here where we have tire pressure monitors and Bluetooth and Wi-Fi, connected vehicles. We have ADAS sensors. So we're cramming many RF systems onto a relatively small platform. And so there's opportunity not only for these systems to interfere with each other, but for the RF systems on nearby vehicles as well as the infrastructure in which these vehicles must operate, there's potential for those systems to cause interference as well. And there are a variety of other platforms. We have military platforms, we have VTOL platforms, satellites, launch systems, ships. And again, it's pretty much anything where we have multiple RF systems integrated onto that platform. We have to think about these interference problems, and we really have to incorporate their broadband performance and potential for interference into the design of the platform. It's never too early to start looking at these types of problems. How interference happens? Well, there's basically two different ways that interference happens. The first is in band, and the second is out of band. And we use this really simple cartoonish-like example here to illustrate both of those. So the blue trace is receiver susceptibility. So here we have an in-band response of this receiver around 200 megahertz. And then we have some mixer product responses. This is a super heterodyne type of receiver, so we can have these out-of-band mixer product responses. For the transmitter, we show the red trace, where we have the fundamental, and then the second, third, and fourth harmonics. So in this very simple example, we have both types of interference occurring. We have the second harmonic of the fundamental, falls in the pass band of this receiver. And then we have the fundamental of the transmitter that's falling in a mixer product for the receiver. So this is interesting, but where we really want to get to is looking at these high fidelity representations of the transmitters and the receivers, not the cartoonish example. So we want to know the detailed performance of the transmitters and receivers, both in band as well as out of band. And while this isn't the focus for our presentation today, the type of data that we're going to show you today, especially for receivers, this could be really useful for understanding how to jam a receiver. Because with this measurement system, we can characterize and identify out-of-band frequencies where receivers, if a signal of the proper amplitude and frequency is injected, will cause jamming to that receiver. So this is yet another application area for this technology. Okay, so a common question that we receive from some of our customers are that all of the RF systems, the transmitters and receivers, have passed their various commercial or military requirements. So Mil Standard 461 is a good example. And so some of the customers believe that because they passed all these unit level tests, that when we integrate those RF systems onto a platform, that everything will be good to go. No problems, no interference issues. And that is simply not correct. And if you look in the appendix of Mil Standard 461, there are some great explanations there. And I'm not going to read through all these right now, but basically what the appendix says is these are guidelines. These are guidelines, but we can't possibly consider every scenario, every configuration for how you might hook up this transmitter or receiver on a platform. So, filters, cables, antenna positions, types of antennas. It's just, you can't consider all of those scenarios. So they're guidelines. And while passing requirements like the commercial standards and Mil Standard 461 is important, it's not the end of the analysis. You still must consider how everything performs when integrated on a platform. Okay, so what's important to model? Well, if we look at this block diagram, on the left, we have a UHF transmitter. On the right, we have a GNSS receiver. There are filters and cables and antennas attached to these systems. And what we need to model is basically everything in this chain, okay? Because every one of these components has the potential to alter the transmission coming out of the transmitter or impact the signals that are seen at the receiver. So we need to model all of these. But again, today what we're focusing on are the RF systems, the transmitters and receivers. Okay, so where do we get this data? Well, the good news is for many of these components, like cables, filters, and amplifiers, vendors are getting better about providing measured S parameters or sometimes simulated S parameters for those components. And so often you can go to their website and you can download directly those S parameters, or you can call the company and if you find the right person, you can have those sent to you as well. So this is getting better, and in those cases where you can't get your hands on that type of data, if you've got a vector network analyzer, these are pretty simple, straightforward measurements to perform. And if your organization can't or doesn't want to do that, then you certainly can have EMA or someone else measure them for you. We also need to know coupling information. So there's a lot of different coupling mechanisms on these platforms. Antenna to antenna is extremely important. We can have coupling between conductors and cable harnesses. This is called crosstalk. We have coupling between cable harnesses, and we have coupling between antennas to cable harnesses and vice versa. So the good news is there are some really powerful simulation tools such as HFSS, EMA 3D cable, SI wave, and other tools that are really well suited for handling these complex problems and producing highly accurate S parameters that we can use in our system level modeling. And again, if you can't simulate them or you have ready access to an anechoic chamber, you certainly can measure those coupling parameters with a VNA. But the radio models, this is the hard part. This is where we don't have all the information that we want. And we don't have it because the vendors don't provide this data. So if you call up the company that makes your RF systems and you ask for high fidelity broadband data, well, very, very often you won't get that information. The vendors just don't have it. They either don't have it or they won't share it. And so typically what you have to do at that point is you turn to specification sheets or spec sheets. But these spec sheets tend to be very high level. They miss a lot of really important details about the out-of-band performance of the transmitters and receivers. And as you can see in these two examples shown here, the parametric models either overpredict or completely miss really important features. So like in the top right image, we show a parametric model for a receiver. We've computed mixer products, and then we went and measured this receiver. Only 3 of the mixer products that were predicted by the simple mixer product model actually exist. So if you use this model in your RFI analysis, you may predict a lot of interference problems that just simply do not exist. And then for the transmitter, you can see the measured transmitter harmonic amplitudes are 20 to 30 dB lower than the requirement for this particular system. And the parametric model completely misses these spurious emissions from the transmitter. Now, a lot of times people will see the amplitude for these spurious emissions and say, well, wait a second, why are we concerned about this? And the reason we're concerned about it is that while some of these are very low amplitude, when you have multiple systems on the same platform, especially if they're operating at nearby frequencies where the antennas couple energy very efficiently, these low amplitude spurious emissions can cause interference. So they are important. We've seen this many times in our practice. And so you need to capture those spurious emissions. Okay, so we measure our transmitters and receivers in isolation. And so what that means is our measurements are performed at the port, the RF port on the transmitter or the receiver. It's not after the antenna or some other device, it's directly at the RF port on the receiver or transmitter. And the reason we do that is very often the same RF system is going to be used in different configurations on the same platform or different platforms. And especially in the design phase, you want to be able to go in and try out different things, to try out, well, what if I use a filter? What if I use this type of amplifier versus that type of amplifier, etc. And so that's why we measure the RF system in isolation. And then that creates a model where you can go into your system modeling tool like the EMIT software product from ANSYS, and you can hook up amplifiers and antennas and filters and cables and multiplexers. And here's an example, where we have two different types of GNSS receivers. We've got a GPS receiver and then one based on the Galileo system. So this is the approach we take for developing these models. So at EMA, we developed the ARM system so that we could generate the high fidelity broadband information for transmitters and receivers that we need for accurate RFI simulations. And there are two really key concepts here. The first is that for transmitters, we need very high dynamic range. So we want to be able to have between 130 to 150 dB of dynamic range in our measurement system. And this is important and necessary because we need to capture those low amplitude spurious emissions and harmonics that the transmitters generate. The second key concept is that for receiver susceptibility, the performance metric is going to vary from one type of radio to another. And so we use whatever metric is appropriate for the type of radio that we're measuring. In some cases, that's SINAD. In other cases, it's carrier to noise ratio or some other metric. And then finally, automation is really key for this system. As you can imagine, many modern RF systems are capable of operating over hundreds or even sometimes thousands of channels. And so going in and measuring many channels in a manual way is just not practical. Okay, and this is especially true for receiver measurements, and that'll become clear here in a moment when we show you some of the examples and demonstrations. Okay, so we'll first look at how the transmitter measurements occur. So we control the system with our software, and so we key the radio to transmit, and then there's a triplexer, which consists of a low pass, band pass, and high pass filter. So the low pass and high pass filters are suppressing the fundamental of the radio to increase the dynamic range of the measurement. The band pass signal goes through the stage here in the middle, and in one case, we're very accurately measuring the fundamental of the transmitter. And in the other case, we're suppressing the fundamental with a notch filter, which allows us to measure the performance of the transmitter close to the fundamental, but not at the fundamental. For receivers, it's a different type of measurement. So in this case, we inject an intended signal and we establish some baseline metric. Again, that could be SINAD, that could be bit error rate, carrier to noise ratio. But we establish a baseline performance metric, and then we introduce an interfering signal out of band. And we vary that interfering signal both in amplitude and frequency while we monitor the performance metric for any sort of degradation. In this example we're showing you here, this is for a SINAD measurement, so we have the audio output signal that we're monitoring the SINAD value. Okay, so now we're entering the demonstration part of this webinar. So we have 5 different examples that we're going to show to you where we have collected data with the arms, and then we are showing you interference problems. Some are relatively obvious and others are not obvious at all. and we'll show you cases where if you use specification sheet data only, you will get the wrong answer. So let's start out here with example 1. We have a VHF transmitter operating at 147 megahertz, and we are going to interfere with a UHF receiver operating at 441 megahertz. Okay, so this is going to be the simplest case that we consider today. You can do the math probably in your head. 3 times 147 is going to give you 441 megahertz, and that's important. But there's some other things going on that are not so obvious, and so we want to walk through this example. So the first thing we show is or are the parametric models. So on the left-hand side is the transmitter parametric model based on Mill Standard 461, and on the right-hand side is the receiver performance, again based on specification sheet information. These are just pictures, placeholder pictures. These are not the actual radios that we measured. So on the previous slide, I showed you the parametric models, and on this slide, I'm showing you the actual measured data. And so I'm going to flip back and forth here so you can see some of the key differences. In particular, pay attention to the harmonic amplitudes, the fact that the parametric model is completely missing these spurious emissions. And in the previous example I showed you, those spurious emissions were around negative 90 dBm. Well, in this case, some of these spurious emissions, number one, this one here is a little hard to see, but it's right next to the fundamental, and it has an amplitude of negative 62 dBm. So these are much stronger spurious emissions than we saw in the previous case. And so this could very easily couple to another VHF receiver operating on the same platform. And then on the receive side, I want you to pay attention to the mixer products. You're going to see that a lot of these disappear, but some are completely missed. These responses out here, close to 2 gigahertz, are not captured in the other model. And then the final thing is the Inband response for this receiver. Now, I'm going to flip back to the parametric models, and then I'll flip again to the measured data. And so you should see some pretty significant differences there between the parametric model and the measured data.
So we have these handheld radios to demonstrate interference from a transmitting channel at 147 megahertz to a receiving channel at 441 megahertz. So they're tuned to completely different channels, but since the third harmonic of the transmitter falls right into the passband of the receiver, you still get interference. And you can hear that audible interference.
Here is the S21 of the low-pass filter we'll use to mitigate the interference. On the right side of the plot, we placed a marker at the location of our third harmonic, and we can see that the low-pass filter will suppress it by a little under 60 dB.
This specific case of interference is unique because there's actually 2 signals contributing to the interference. We've hooked a low-pass filter up to the transmitter to block that third harmonic from getting to the receiver, but the fundamental of the transmitter actually falls into a mixer product for the receiver as well. So we're going to show that with this low-pass filter that we still get interference. So you can still hear the audible interference, and it's a little weaker because the signal levels aren't as strong.
Okay, so that was a nice demonstration performed by my colleagues Curtis and Juan. And now I want to show you how we take the measured data from ARMS and we bring it into a system modeling tool that allows us to understand the root cause of the interference between these systems. And that system modeling tool is the EMIT software from ANSYS. So there's a lot going on in this plot here. So what we're showing, the blue trace is the measured receiver response. So this should look familiar. We've just zoomed in a bit here from the previous plots. And then the orange trace is the power level present at the receiver port. Again, the RF port on the receiver. And the black trace is the EMI margin. EMI margin tells us whether or not interference is occurring or not. So anytime that EMI margin is positive, that means the interfering signal has exceeded the susceptibility of the receiver at that frequency. So we see two cases here where the EMI margin is positive. The first one is due to the third harmonic of the 147 megahertz transmitter. So we have this really large interference problem of 52 dB. And then over here on the left, this is what Curtis was talking about at the end of the video. The fundamental is falling of the transmitter is falling in a mixer product of the receiver. So we have two different problems, and the second one is not, without measured data, this is not obvious at all. So as Juan pointed out in the video, we then introduced a low pass filter because we weren't aware that this, let's just assume that we weren't aware about this problem with the fundamental and the mixer product. And so we're getting about 60 dB of insertion loss or rejection due to this filter, which reduces this interference problem to the point where the third harmonic is no longer causing interference with the receiver. It is actually about 8 dB below the susceptibility of the receiver. However, as demonstrated in the video, we still have the case where the fundamental of the transmitter is falling in this mixer product, and we still have a relatively large interference problem that would need to be mitigated. Okay, so moving on to example 2. In this case, we have a UHF transmitter that's operating at 390 megahertz and a GNSS receiver that's operating at L1. And what we're going to show in this example is the importance, again, of measured data, especially in this case for the receiver's performance. So again, we're looking at results within the emit software. So we've loaded up the transmitter and receiver measured data. Same as in the previous plot, the blue trace is the receiver susceptibility. The orange trace is the power level at the RF port, and the black trace is the EMI margin. Now again, I'm going to flip back and forth between a couple of slides here to show you the performance predicted by the specification sheet versus the measured performance. So the data you're looking at here is the measured receiver susceptibility as characterized by the ARMS system. So in this case, we're predicting an EMI problem with about a 17.4 dB amplitude, so a pretty significant interference problem. However, if we had not used measured data, we would miss this interference problem completely, okay? Because the spec sheet for this receiver says it has a much narrower response and frequency than the actual measured data shows. And in fact, using the specification sheet data in our simulation, we would say that we have 34.4 dB of margin, meaning the interfering signal is 34.4 dB below the susceptibility of the receiver. Let's take another look at this. Now, here is the measured data again, and you can see how broad this response is compared to what the specification sheet showed. Okay, in example 3, we're looking at a 430 megahertz transmitter interfering with a UHF transmitter, receiver operating at 453.175 megahertz. So this is a case where it's not a harmonic, so it must be some other mechanism that is causing the interference to occur. And again, we start out by showing the spec sheet models that were built for the transmitter and receiver. And
so here's another interference case where we have our receiver tuned to 453.175 megahertz. And with the down converter in this receiver, there's a mixer product that falls right at 430 megahertz. So we've got Juan's radio tuned right to 430 megahertz, and we're going to demonstrate that you still get interference between these systems.
Ready?
Yeah. So as you can see, there's a very audible interference there, and that's due to that mixer product.
Okay, so what's going on? Well, as Curtis indicated, it is indeed a mixer product. What's interesting is when we use the parametric data or the spec sheet data for the transmitter and receiver, we predict two different interference problems. Okay, the first interference problem is due to the fundamental operating at 430 megahertz, falling in a mixer product of the receiver. But we also predict an interference problem due to the second harmonic of the transmitter at 860 megahertz, falling in another mixer product. So if all we had was this specification sheet data, we would say, well, we have two interference problems that we need to mitigate. But when we actually go out and measure the transmitter and measure the receiver, what we see is that most of these mixer products for the receiver just don't exist. However, this one does, and that one lies right at 430 megahertz, which is our transmitter frequency, and this is why you heard the audible interference in the video that Juan and Curtis just showed us. Okay, now in example 4, this is a demonstration to emphasize the importance of automation in our measurement system. So this was our 441 megahertz channel, receive channel that we showed you earlier. And as you can see here, there's a really significant mixer product that occurs at 348.3 megahertz. So we're going to show you, Juan's going to demonstrate with the signal generator. We're going to inject a signal directly into the front end of this receiver and show you the SINAD value and how he has to vary the power level to determine that threshold where we go from no interference to interference. And keep in mind, this is one frequency. Okay, for a measurement like this, we're considering many, many different frequencies at which we have to do that sort of measurement.
So for this setup, we're using the same radio that we had before, operating at 441 megahertz. So this top signal generator is our intended signal operating this 441 megahertz. I've set the power level in such a way that the SINAD measurement is around 20 dB. The second signal generator on the bottom is our interfering signal. We had previously measured on this radio that we have a mixer product at 348.3 megahertz. So I've set this interferer to 348.3 megahertz, and then right now I have it off. So we have the baseline of the intended around 20. As soon as I turn this guy on and start increasing the power, you start to notice that the SINAD degrades. The metric that we used when we did this measurement was a baseline of 20 dB, and we dropped it down to about 12 dB to figure out our interferer. So as we start decreasing it down, or increasing the power, start to notice that the SINAD keeps going down. It's right around here is around 12 dB SINAD. So we're measuring about minus 46.7 out of the interfering signal generator. In the previous measurement, we measured minus 47.4. So within a dB of the previous value.
So as you can imagine from that previous video, automation is really crucial for characterizing a receiver's performance over many frequencies. And keep in mind that with each one of those frequencies, you're varying the amplitude of the interfering signal while monitoring the interference metric. And so there's a lot of automation that goes into that process to speed it up. So in our last example, we're going to consider an LTE modem as our transmitter, and we're looking at band 13, and then we're going to consider a GNSS receiver as our victim. And this system, the GNSS receiver, is tuned to L1 which is 1575.42 megahertz. Okay, so LTE is not a fixed frequency. The frequencies or the transmitted signal adjust. It jumps from one frequency to the next over some defined frequency range. And so in the video I'm about to show you, Juan establishes a carrier to noise metric for the receiver of about 40 dB. And then he turns on the LTE modem, and we look at the LTE harmonics, and you'll see them jumping around in frequency, and you'll also see degradation in the carrier to noise as those interfering signals are introduced. And again, I show a plot down here. So again, keep in mind, LTE is not a fixed frequency. This is actually moving around in frequency. But what's important here is to consider the spec sheet response of this GNSS receiver versus the measured response. And for this frequency in particular, if we were using the spec sheet model for this GNSS receiver, we would say there's no problem, no interference here. But when we use our much more accurate measured data, then we are predicting interference and significant interference, as you'll see here in a moment.
For this scenario, we have an LTE modem as our transmitter and a GPS radio as our receiver. On the left side of the screen, we're monitoring the carrier to noise of our GPS signal, which operates at the L1 band or 1575.42 megahertz. On the right side of the screen, we're monitoring the second harmonic of LTE band 13. LTE band 13 transmits between 777 to 787 megahertz, meaning that the second harmonics lie between 1554 to 1574 megahertz. So without our LTE signal, we can see that our GPS carrier to noise is staying consistently around 40 dB hertz. When we start transmitting our LTE signal, you can see that the second harmonics start to come up and that our carrier to noise on our GPS signal begins to degrade. When I stop my LTE signal, you can see that with enough time that the GPS signal goes back to our baseline of about 40.
Yeah, and as I've indicated before, we need this high dynamic range in our measurement system because the interfering signals can have very low amplitude but still be problematic. And so I just did a screen capture here of Juan's video, and you can see these signals, they're below negative 80 dBm, and yet they're causing interference to this GPS receiver. So again, dynamic range in our measurement system is extremely important. Okay, so that was the last example. I just want to spend a moment here and talk about platform level system integration modeling. And the approach that we use here at EMA, it's a combination of our ARMS measurement system, certainly, along with some very powerful simulation tools. So, and these simulation tools are powerful because there is a workflow where data goes from one tool to the other in a very seamless sort of way. So ARMS data can be brought in and used to drive antennas in HFSS. We can generate near field sources from HFSS for antennas, bring those into EMA 3D cable. We can bring near field sources for PCBs from ANSYS SI Wave into EMA 3D cable. And then EMA 3D cable can be used to compute S parameters for crosstalk, for cable to cable, antenna to cable, a variety of scenarios. And all of this data goes into the EMIT software. So EMIT manages a lot of data for antennas and filters and amplifiers and RF systems. And it's within EMIT is where we're able to pinpoint the interference and then come up with an effective a way to mitigate that interference. So again, this is just ARMS is certainly important. It is part of the overall solution for solving these types of problems. Okay, so in summary, the cost of RFI in your system is real. Whenever we have an engagement with a customer, we encourage them to start looking at RFI as soon as possible. And the reason for this is it's not job security. It is because the sooner we identify these interference problems, the more effectively we can mitigate those problems. Nobody wants to find an issue at the 11th hour right before you're ready to bring a product to market. This can result in things like parking lots full of brand new cars that can't be sold because they didn't pass their various tests, or grounded aircraft. No one wants missed deadlines or bad publicity or lost revenue because of an interference problem. And in some cases, these types of interference problems can cause crashes and potentially loss of life. So this is really serious. It's important to look at RFI early and to get it right. And as part of that, measured data is critical. You can perform RFI analysis with spec sheet information, but you have to keep in mind it's not as accurate as it could be. And with the ARM system, we're able to generate that high fidelity measured data where when you finish the analysis, you have a high degree of confidence in the results. So EMA is here. We can measure your RF systems for you. You can send your RF systems to us and we'll characterize them, send the data back to you along with your equipment. We can also perform measurements at your facilities, which we're happy to do. So if there's anything we can do to help your company or organization, please don't hesitate to reach out to me directly, or you can send an email to our company using our online form on the website shown here. And before we go to the Q&A session, I just want to acknowledge some people. Curtis Crockett and Juan Arambula from EMA. As you saw today, they played a critical role in this webinar, generated a lot of really interesting examples that we showed today. So thank you very much, Curtis and Juan. I appreciate the help. And also definitely want to recognize NavAir. The development of the ARMS has been funded through a phase 2 small business innovation research contract provided by NavAir. So thank you to the Navy, especially to NavAir, for this opportunity. And with that, I will stop and we'll enter the Q&A session of the webinar.